Hey everyone, and welcome back to the channel. So today, albeit the fact that I don't yet have 50,000 subscribers, consider this sort of a de facto 50,000 subscriber special. And yeah, I guess we'll go ahead and get into it. The gist here is that I want to make, I guess, an introductory video for those who are really not sure where to start when it comes to systems design. On this channel in the past, I've been especially critical of people that post too much redundant stuff. And I guess I am kind of guilty of doing that, but I understand that there are a lot of people who come onto YouTube or come onto the internet in general looking for kind of a starting point to get involved with this stuff when they're starting to hear about these interviews and prepare for them. I was in that position a few years ago, and I think this would have been really useful for me to have. I think there are a few of them out there on GitHub, but maybe some of them miss some essential topics. And also I think towards the end of this video, I'm also going to try and break down a little bit kind of the common patterns across systems design interview problems so that you can recognize those in the same way that you would with something like a lead code problem, and then try and go ahead and implement the patterns that you've seen in the past so that you can come up with an ideal solution. So again, thank you all. I really appreciate it. I don't know how long this video is going to take, but hopefully not too long, because I want to be able to clickbait it and say that it's only going to be an hour. So without further ado, let's go ahead and get started. Alrighty, so you may think to yourself, oh, Jordan, where's the iPad today? You got to be able to draw out examples. Well, frankly, there are 80 slides in this slideshow, and if I were to draw all of those out, this video would never get made. So I'm going to pay homage to my original style of making videos via the old consultant-style PowerPoint. And if you hear my keyboard clicking away, it's not because I'm looking up anime girls on the other monitors. It is simply because I am switching the slides. Also, I'm sorry, I'm probably not going to look at the camera for most of this because I am going to be doing a lot of reading off the slides because I simply can't remember everything that I've talked about. Let's go ahead and get started. Cool. So, first thing that we're going to quickly go through is actually giving a systems design interview, right? This is your first time, you're up there, what are you going to go ahead and say? Well, pretty simple, figure out the requirements of the problem. Now the requirements are obviously going to be very broad, right? If I tell you to build Facebook, you're not going to build every feature, you're going to build out a subset of the features. Typically they'll want you to focus on one particular feature because it is challenging to build and challenging to talk about. So, for something like Facebook, they might say build me Facebook newsfeed. They're not going to say build me Facebook Messenger, build me Instagram Reels, build me Instagram Threads, on and on and on and on and on. No. Identify with your interviewer which parts of the problem are important, go from there. Next, they may want you to do some back of the envelope calculations. These are the type of thing where basically you don't always necessarily have to provide them, and if you do, they can be pretty crude, but you're ultimately trying to get an estimate of maybe the number of reads relative to the number of writes, which path you want to optimize for, whether it's read optimized or write optimized. And maybe just if there's a ton of storage, whether you're ultimately going to need to do things like partitioning or replication or anything like that. These are all terms that we're going to discuss later in this video. Next is going to be API design. So again, maybe if you're talking about like a meta product interview, it might be a little bit more important here, but for the most part, just give the general API of all the endpoints that you might have in your system, and then finally we'll jump into the architectural design. Cool, so let's go ahead and look quickly at the table of contents for this video. I'm going to put timestamps for all of these, a lot of basic concepts first, and then if you're already familiar with these basic concepts, we have a bunch of interview patterns. So the reason people are always asking me to make more systems design interview problem videos, and I'm like, no, I don't want to, is because of the fact that I think they're mostly redundant. The reason being that I think probably 90% of the suggestions that I get fall into generally one of these buckets, or one of these like 7 or 8 buckets that I cover. And I think that just being able to identify which bucket a problem is in is probably 90% of the challenge. So we're going to go ahead and talk about those later in the video, but for now, let's go ahead and get started with some concepts. Cool. The first thing that is probably the most important that we have to know about when it comes to any systems design problem is the nuances of how a database works. So databases are just durable systems to let us store application state. They do so by storing data on a hard drive. And so basically the idea here is because we have some mechanical arms spinning around a disk, we always want to keep our related data that we're reading and writing together as close to one another as possible. So what this is really going to look like is, let's say we want to read related data. If we want to go ahead and read all keys, from let's say A through C, because all of our keys are sorted alphabetically, that's going to be a much faster read than if all of our data is just scattered randomly on disk. And so that's kind of the premise behind something like a database index. So basically the idea here is if we don't have an index, every single write, the way that we would really optimize that is just by putting it in a write-ahead log. So a write-ahead log is just a sequential log of data on disk. The reason we would do this is because, like I mentioned, sequential operations on a hard drive are always faster than random ones. And so if we just want to optimize for writes and there's nothing we can really do to optimize for reads, well, let's just go ahead and make a write. So what does that actually look like? Well, basically, we've got x equals 5. Let's say that's the first entry in our write-ahead log. I can see that my camera is also tweaking out right now, and I didn't realize that. But because I'm a one-take gang, I'm not re-recording this. Okay, x equals 5 over here. Let's say I want to make the next write. Oh, y equals 10 all of a sudden. Oh, z equals 22. Okay, so we're writing sequentially through this log. Then finally, let's say I want to go ahead and rewrite the key for x. We can see now that x is actually going to be written again. Because why would we go all the way back to the beginning of our write-ahead log? That's not a sequential write. We'll just write it over. So then you say, okay, well, how can we do reads? If we're going to do reads, we just read from the bottom of the write-ahead log and find the latest value for the key to find its proper value. So the problem with this is that that's a sequential scan, right? If there are n entries in the log, this is an O of n read. So what do we want to do to improve that? We want to add something called indexes to our database, where an index is basically going to allow us to read very quickly when we're searching for the value of a particular key. Cool. So quick fundamentals, there are a few different types of indexes. Let's discuss them. The first one is called hash indexes. So hash indexes is where we keep all of the keys in memory. We probably keep their corresponding address on disk in memory with them so that we don't take up too much space in memory. And then again on disk, those values can be wherever. So we can see that as a result of using a hash map, if you're familiar with your data structures, you're getting O of 1 reads, O of 1 writes, which is great. At the same time, your key set needs to fit in memory, and we have poor support for range queries. The reason being that X, Y, Z are not necessarily going to be ordered on disk, or rather the rows for X, Y, Z are not going to be ordered on disk, so our data might not be contiguous. The next type of index that we have is going to be B+ trees. Basically, we're going to organize a tree of all of our keys on disk, and the idea is we basically use a bunch of pointers to figure out where a key lies. So you can see in the diagram on my left, if I'm searching for keys between 1 and 11, I'm going to take the pointer that is, between the 1 and 11 key. And then if I'm looking for all the keys between 1 and 5, I'm going to go left again to that disk page that holds the data for keys 1, 2, 3, and 4. So basically, we have a bunch of pointers on disk, we organize our data in a tree, and what's really nice about this approach is that you can see that the data for related keys, so 1, 2, 3, and 4 are all very similar to one another. They're, when you sort the keys, they're next to one another. Their data is also next to one another. And what this allows us to do really nicely is something called range queries, which is a very common use of databases, right? Maybe I want to get all the values for keys 1 through 4. Now, instead of having to read a bunch of different places on disk, all of those values are next to one another, and it should be a fairly fast read. Because of this tree structure, again, think back to your data structures here, and all of our reads are coming from there, and all of our writes are going to there, we are getting logarithmic time complexities. Cool. We also have a third type of index, this will be the last one, that we'll call LSM trees and SS tables. So basically, for something like this, all of our writes first go to an in-memory binary search tree, and then from there, once that tree gets a little bit too big in memory, we basically take it and we flush it out to disk in a sorted file. So what this means is that we can have multiple different sorted files containing our key value pairs. It also means that we can still have a tree with data in it. So even though that makes writes fairly fast because they're first going into this LSM tree, what they're going to do right after that is when we want to actually read data, we first search the LSM tree. If it's not in there, the key value pair, then we go ahead and check out every single SS table from newest to oldest. In the background, you can also optimize this process a lot by merging together a bunch of the SS table files in a process known as compaction. There are a bunch of other data structures that you can add, like sparse indexes or Bloom filters to make this process faster. But again, as an overview, I don't think it's too important to cover that right now. Cool. The next thing to talk about here is going to be transactions. So transactions are a term that you may have heard a lot about, but the main gist here is in databases, these are multi-threaded machines, right, or multi-threaded programs. And so you can't necessarily rely on just being able to go ahead and make writes all the time without having to worry about race conditions. So we often hear this term ACID to describe transactions, and what this really means, I'm not going to go through the full acronym for ACID, it really means that these writes that you're making to your table are atomic, meaning that if I'm writing to multiple rows at once, they're all either going to succeed or they're going to fail, and they're also serializable, meaning that we effectively aren't going to have any concurrency bugs to worry about. It's going to look as if, one thread we're making all of these writes. So in reality, how do we implement atomicity? Well, basically what every database does is they have something called a write-ahead log. Now we discussed the write-ahead log earlier. It's literally you just take every single write that you're making into the database and put it into some sequential log on disk. The reason we do that is then because when we start a write, we put it in the write-ahead log. When we complete a write, we write that particular entry is now committed. This means that if the database fails before the entry is committed, we can actually go ahead and start back up, read from our write-ahead log, see that we had an uncommitted write, and then go ahead and apply it again. Serializable, on the other hand, is a little bit harder to implement, so we'll talk about that right now. Basically, there are a few different ways of ensuring that a database is serializable. One way is literally just running it on a single thread. I don't want to go into too many specific database examples in this video, but something like VoltDB does actually do this. We've also got pessimistic concurrency control. In this case, we're basically using a bunch of locks to stop conflicting transactions from messing with one another. If I'm reading a bunch of data and then I'm making a write based on the value that I read, we need to basically make sure that I have locks applied on all of the rows that I could have read so that anyone else who's trying to modify them or do anything like that cannot actually proceed. On the contrary, we also have optimistic concurrency control. This is a little bit different in the sense that rather than having transactions directly block one another, they can basically all proceed until they're right about to commit, and then they check whether basically the premise or the predicate or whatever they read has since changed, and if it has, it means that their transaction is no longer valid and they need to abort it. So something like optimistic concurrency control is really nice when we don't have a lot of contending transactions that all want to grab the same locks, because of the fact that now there's no overhead to grabbing the locks whatsoever. Pessimistic concurrency control, on the other hand, is going to be better when we basically have a lot of contending transactions, because then we're just blocking them rather than running the whole transaction and then aborting right before it completes. Cool. So I guess another question from here is, okay, well, we have this concept of database transactions. Does every database support them? And the answer to that is actually no. Typically, most SQL databases will do so because they tend to be a little bit older, and even within all SQL databases, it's not necessarily the case. But if you're talking about like MySQL or Postgres or something like that, you can definitely use transactions. That being said, one trend in the last 10, 15 years has been for these NoSQL databases to come around and stop supporting transactions. The reason being, transactions are expensive. And so if you don't necessarily need to use transactions for your particular use case, maybe it's actually going to be faster to just drop the ability to support them, and then the database can run a little bit faster. Transactions are really, really useful if you have to reason about concurrency because it makes things a lot simpler to think about, but at the same time, they're going to make reads and writes slower, right? We're either aborting potentially a lot of writes, or we are potentially going to be adding a lot of locks to our system. Cool. Another piece that I want to talk about when it comes to databases is actually going to be row-based versus columnar storage. So basically, like I mentioned, the whole really nice thing about something like an index is that it keeps related data together on a disk. And so even within multiple different keys, what about thinking about just one row, right? If I'm a user and I'm on Facebook and I want to access my own profile, it would probably be good if all the fields related to my profile were next to one another on disk, because when I'm doing a read, I'm going to access all of those at the same time. However, for something like analytical queries, this makes a lot less sense, right? Because typically for a big analytical query that maybe a data scientist might run, you've got a lot of different columns in a massive table, and you really only care about one or two columns. You're reading probably the whole thing, and you're performing some sort of aggregation or grouping on that column. And so for this type of use case, something like a column store is actually going to support you better. And so in a column store, the idea is rather than store every single row together on disk, take the values within a particular column and store those together on disk. The nice thing about this is that, for one, you only have to read a subset of the data if you're only interested in a couple of columns at a time. So that's going to speed things up. Number two is that you get all of these nice compression benefits as a result of the fact that all of the data within a column is really similar to one another. Cool. Another piece to talk about is data serialization frameworks. So technically, this could be part of the database chapter here, but I think I'm going to make it its own. Very simple. If we have a bunch of data and we need to represent it on disk or over the network, basically as ones and zeros, how do we want to do so? Well, sometimes you have no choice. If you're supporting a flexible schema, maybe you have to use something like JSON, right? I could be sending any arbitrary object with JSON because it's literally just like I put the field name in quotes and then I put the object right after it. And that's all really nice. However, if you are using strongly typed schemas, you could actually introduce some other technologies here. One really good example of these would be something like protocol buffers out of Google, where basically you create a predefined schema such that you can actually use objects that fit this schema in multiple different types of code. You can send them over the network, you can store them in a database, and then actually on the wire or as binary, you don't have to then include all of the field names in that message, thus making them quite a bit smaller, right? Because if I know that field name corresponds to tag number 1, as you can see in my diagram on the screen in the bottom left, it means that you basically only have to include 1 to say, hey, this is the name field, and then the actual value of the name field, as opposed to doing that. And so it saves you a lot of space. Cool. So we've made it through databases, we've made it through data serialization. Let's go ahead and talk about replication. So basically, if we have a database, it's going to fail, right? Especially if we have a lot of them. Hardware failures are common. Things just break, especially when they're in big data centers. This happens all the time. And so basically, we want to be able to do two things. One is we want to protect against database failures, and two is that we want to make our databases as fast as possible. So what can we actually do to do this? Well, we do something called replication, which is really just having multiple copies of the data. So replication is going to allow us to potentially withstand hardware failures, and this is going to change depending on how we do the replication, and also improve our database performance. Same deal, depending on the type of replication you do, this is going to change. And so the idea is that you've got some sort of source database or maybe one database that gets a write, and then it is sending that data via something called a replication log to the other databases. And the replication log is very similar to the write-ahead log. It basically just has all of the incremental operations that are being performed on the database. X equals 5. Nope, never mind, now X equals 10. Nope, never mind, now X equals 15. You can put those all in a replication log and then apply them downstream on replicas. Cool. So what is a pretty big distinction in replication is synchronous versus asynchronous replication. So synchronous replication, and sometimes you'll hear this called strong consistency, is basically that on a write, all of our replicas are going to have to process that write before the writer actually sees that their write succeeded, right? So that means that when I write, every single one of the replicas is now up to date, which is great because you don't have to risk any reads of stale data. On the other hand, asynchronous replication is, you write to one particular replica. At some point in the future, it's going to send that write to the other replicas. However, the problem is now if someone reads from one of the other replicas, there's no guarantee that that data is going to be there. That's known as eventual consistency. You potentially have to deal with stale data. Depending on your application, sometimes that's totally fine. Cool. So let's go through the actual types of replication. And in all of this, I'm kind of assuming we mean asynchronous replication because the truth is synchronous replication is not very viable due to the fact that if any of those replicas goes down, now all of a sudden we can't make any writes. So single leader replication. Basically, we've got one leader database that accepts all the writes, and then reads can be served from any of the follower databases. So this is really simple. I would think of it as kind of like the default type of replication, but it's got a couple of cons. For one, write throughput is actually going to be limited to the leader replica, right? Writes can only go to one place. Number two is that if the leader actually fails, we need to go ahead and pick a new leader, and so that's going to lead to some downtime whereby we can't submit any writes. And number three, basically, I guess I kind of already said number three is that, when we're performing this failover, when the leader goes down, we can't perform any writes. And also when a leader does go down, because of the fact that we're doing this asynchronous replication, it is possible that the follower that becomes the next leader doesn't actually have all of the data on it that the leader had, and then we might lose a couple of our writes. Okay, next thing we're going to do is talk about multi-leader replication. This one's going to get a little bit more complicated, so bear with me. Basically, the idea is for a given particular key, you can have multiple leaders that are able to serve writes for it, and then all of those leaders can also serve reads too. So this is really nice because now we can write to multiple places, right? We get increased write throughput. On the contrary, we now have write conflicts because if I write to one of these leaders saying x equals 10, and I write to another one of these leaders saying x equals 20, well, what's the actual correct value for x? Kind of hard to say, isn't it? So basically, there are a few different ways to deal with this, because eventually these leaders are going to synchronize with one another, right? You don't just write to them and then they hold their own data and you never merge them together. Eventually these guys will talk to one another and they're going to try and figure out, hey, for this value X, what's the actual, or for this key X, what's the actual proper value? So there are a few different ways to decide what the proper value is. Number one is last write wins. Give everyone a timestamp and then all of a sudden you're good to go. Timestamps are always going to choose one of the writes to win, and that's really nice. On the other hand, timestamps in distributed computers are pretty much arbitrary. I mean, they're not arbitrary, but ultimately you can't trust timestamps to be perfect because the way that actual clocks in a computer work are such that they can like drift a little bit by a couple of milliseconds at a time. And so as a result of that, there's no guarantee that the write that you do pick is actually the one that occurred later. And even if it is, when one of them wins, you basically just lose any record of the other write ever happening, and then you forget about it. And so even though this is really simple to implement, it does have some downsides. So what are some other ways that we can deal with this? Number two is going to be storing siblings. Now, please, again, if you don't fully understand this example, no worries. I talk about it a lot more on this channel. That's why I'm making this video, so that you can go watch my other videos. Basically, the gist is, a concurrent write, so two writes are concurrent when they basically don't know about one another and they go to the different leaders. And the problem with that is that you don't just want to throw away one of the concurrent writes. Ideally, you want to keep that information so that you can at least use it somewhere later down the line, right? We never want to lose information, especially if a user has written it and they think that it is written. So the idea is, if we can detect two concurrent writes, we want to basically be able to store both of them, and then someone later, when they read the data, can see both of those writes, figure out a way to merge them together, and then write back to the database such that now there's only going to be one value. So let's look at the following situation. We've got two leaders, right? They both have x equal to 0, and no one has written to them yet. So let's say I write to the leader on the left, which we'll call leader A. So you can see now x is equal to 10. So we do something called version vectors to actually determine when we have a concurrent write. And so a version vector is very simple. It's literally just a very small array of how many writes has been processed by each leader. So this is going to allow us to determine when two writes are concurrent. So the way that it works is every time I write to a leader, it increments its own entry in its own version vector. So when I write to leader A bumps its index for leader A. So I write x equals 10 to leader A, it bumps its version vector. And then let's say we end up having some sort of synchronization step, right, where leader A tells leader B, hey, here's what I think the value for x is. You can see that when leader B receives leader A's value, it also merges in leader A's version vector into its own local version vector. And so what this really means is that when we're merging version vectors, we keep the highest number for each replica. So if I'm leader B, I can see, oh, you know what, I have an entry for A coming in that's higher than I've seen. Let me go ahead and change my version vector such that I'm up to date with that, and also change my write such that I'm up to date with it. Let's say someone now makes a write to leader B. Leader B is going to bump their local version number, right? So we're going to say, oh, B has now seen one write, and the value corresponding to that is x equals 20. Let's say, however, that in the meantime, leader A gets another write, and leader A now is going to bump its own version vector to number 2. So notice, if we actually look at the state on both of these leaders, x equals 30 versus x equals 20, these two writes are concurrent, right? Because the person who wrote x equals 20 is not aware of the person who wrote x equals 30. These are concurrent writes. They should be stored as siblings in the database and handled later. The way that we know that they should be stored as siblings is by looking at the version vectors. So you can see on leader A, the A entry is greater than the A entry on leader B, and on leader A, the B entry is less than the B entry on leader B. And so because we have these kind of interleaved version vectors, that is going to indicate that one write is concurrent with the other. If one of the version vectors were strictly greater than the other at all of the elements, then those writes would not be concurrent. One would be more recent than the other. So let's say we go ahead and sync up. Since our writes are concurrent, A knows it needs to store both. And so when B eventually synchronizes back to A, what's going to happen is that we go ahead, merge the version vectors, but A is going to say, okay, I need to store both of these things. And so this way, someone else can read the data later, see, ooh, it's 30 and 20. What should I write? Ooh, maybe I'm going to write 25. Cool. So again, if that's not that clear, no worries. It's not an easy concept, and debatably, I shouldn't have even covered it here, but we did it. Fuck it. Let's continue. Replication, automatic resolution. So the third option for how we deal with multiple leaders and conflicting writes is we actually automatically resolve, basically, we resolve conflicts on the database. So rather than having a user basically read the data of stored siblings and then write them back, what we'll do instead is the database itself is actually capable of merging those two values. So basically, if you think about it, to some extent, the actual version vector that we've seen in the prior slide is a good example of this for building something like a counter, because it tells us how many writes total that we've had on each leader, and it's an eventually consistent way of doing so. You can also basically perform automatic resolution for things like set objects, for sequence objects, but of course, these can't get too complicated, right? Because they have to be built into the database beforehand. It's nice when a database provider provides this for you, but if you're really trying to do some complicated stuff, you're probably not able to do it, and then you're going to have to store siblings. Cool. Okay, so we've gone through multi-leader replication. Let's go ahead and now go through leaderless replication. Basically, the idea here is that rather than basically writing to just one place at a time and reading from one place at a time, now we're actually going to write and read from many places at once. So the idea here is we don't have a leader because we're writing to multiple places, and so that means there's no big failover if a leader goes down, right? We're always available, we can always write somewhere, which is really, really nice. And then I guess the problem or the con of this approach is that we have longer tail latencies. If I need to wait for 3 nodes to respond to my write before my write is considered committed, then what that means is that I'm basically bottlenecked by the slowest of those 3 nodes. And the same thing applies for reads. So the question is, well, how many replicas do we actually have to write to and read from for one of these operations to be valid? So this is where we introduce the concept of something called quorums. So let's say we have n replicas in our setup. And for us to consider a write to be valid, it has to first make it to w replicas. And for us to have all of the data that we need to actually make a successful read, we need to read from r replicas. A quorum is when that w plus r parameter is greater than the n nodes. And so if this occurs, then we have something known as a quorum. So basically, as you can see in the image on the bottom left, if we have 3 replicas in our cluster, where if we set w equal to 2, meaning we have to write to 2 replicas every single time we try to write, at least 2, and if we set r equal to 2, meaning that we have to read from 2 replicas every single time that we tried to read, again, at least 2, we know that those reads and writes will overlap by at least 1 replica on each set, and so one of them, in theory, should have the up-to-date data. From there, it's just a question of, okay, well, now we have multiple different values on our reads. How do we actually determine which one is the correct value? Well, we have kind of discussed this already. We can use something like a timestamp, we can use something like a version vector to try and get a better sense of which write is the actual most up-to-date one, and that way a reader can see the up-to-date data. Cool, we finally made it through replication because I think, frankly, that's going to be the most complicated part of all of this by a long shot. Let's go ahead and talk about sharding. So the idea here for sharding is that when we have a database and there's too much load on it, we're eventually going to have to split it out, right? That's kind of the theme of distributed systems. You need to split this work between multiple different computers, otherwise it's just not going to work properly. Facebook can't be run on one computer, and that's not going to fly. So the main kind of idea when it comes to sharding or partitioning, whatever you want to call it, is that when we ultimately make our database shards, we want the majority of our read queries and the majority of our write queries to only have to interact with one shard at a time. If they have to interact with, say, 10 different shards, then basically an operation cannot be considered completed until the slowest of those 10 is done responding. And so keeping all of our data accesses and mutations to one place is the way to keep things as fast as possible. We also want to ensure that we don't have something called hotspots, where hotspots are shards that have a disproportionate amount of either the data or the number of requests going to them. So how can we go ahead and do that? Well, the question, I guess, is how should we actually shard out our data? If we have a database and we've got a bunch of key value pairs, how do we want to go ahead and partition them? Well, one thing we can do is just by doing so by the range of keys. And you can see this image below. If we have a bunch of different names, we can just partition them by a key range. So this is really nice if we want to be able to support range queries still, right? Because it means that similar keys to one another are going to be on the same shard, and we don't have to make a big distributed query. That being said, it also means that we're more prone to hotspots. Especially for names, for example, there are a lot more names that start with A or maybe J than there are that start with Z. So ultimately, you have to be very careful here. What else could we do? Well, we could do something called basically the range of the key hash. So for a given key, basically all you have to do is take the hash of it and then shard it based on the hash of it. So why do we actually go ahead and do something like this? Well, the idea is that a hash function should, in theory, evenly distribute a range of keys, and as a result, we should get better balancing. At the same time, the downside of this is that, if you want to query all of the names that start with A, those hashes are all going to be completely different, and now we can't easily run a range query because we're going to have to go ahead and access a bunch of different database shards. So it's not super easy to do this, but nonetheless, oftentimes it is going to be the correct approach if you don't need these big range queries. Cool. So one thing we don't want to do in this particular situation is we don't want to take the hash of a key and take it modulo the number of shards and then send it to the shard that it ends up at. The reason for this is that, let's say I add one more shard to our cluster. Now the majority of our keys are going to have to be shuffled to different shards, right? Because that's how modulo works. If you think of, I have 12 keys, and right now all of them can be in one of 3 nodes based on modulo 3, and then I now make it modulo 4, a majority of those keys are moving to a different node, and that's not going to be very good. So what do we do to mitigate this? Well, there's a separate algorithm called consistent hashing. The main idea behind consistent hashing is that you basically organize kind of the hash range, so basically every possible hash value of a key on some ring, and then when you find a key, you take the hash of it, you walk clockwise around the ring until you find a machine's location on the ring or a shard's location on the ring, and that is basically going to tell you what shard a given key belongs to. The reason we go through the trouble of doing all of this is that it leads to less rebalancing when we actually add or remove a machine from the cluster. Let's imagine that we added a machine at that vertical blue line on the circle, so right at the 12 o'clock position. Basically, what that's really going to be doing is just taking a subset of the keys that would have gone to machine 2, and now they go to that vertical line new node. And so what this does is it just minimizes the amount of nodes that have to actually send their keys around. Again, this is an oversimplification of things. In reality, there's a little bit more work done to ensure that all of the nodes do have a relatively even balance of the keys, but this is just going to allow us to, dynamically change our cluster size without having to send keys all over the place all the time. Okay, another thing that I want to touch upon is local secondary indexes. So we know what an index is, right? An index is basically just sorting data in a database by a particular key, so that when we say, hey, find me all of the rows that have this particular key, that's really fast. Simple enough. We also know what secondary indexes are. It's the same thing on a database, but just on a different field, right? If I have a bunch of different users in a table, maybe I want an index on user ID, and then maybe I also want an index on their age, because maybe I want to be able to search for all people whose age are 24 or something like that. That being said, this gets a little bit more complicated when you're doing sharding. So the idea here is basically that a local secondary index is the same exact thing as just adding an index per shard. So it means that rather than having an entire view of all of the rows in the database, your local secondary index only applies to the rows that are on that particular shard. So this is nice in the sense that it doesn't really slow down writes very much, right? Writes are still going to go to one individual shard, but at the same time, if you want to actually read on that key, let's say I want to find all of the people, maybe our primary index is based on a user ID, but then I want a secondary index on the actual age of every single user. If I want to find the age of all users who are 24, now I have to read from every single shard and use their local secondary index, and so that's going to be a lot slower for reads. What can we do in contrast? Well, there's something known as global secondary indexes. The reason they're called global is because they basically index the entire global table, and then they themselves are partitioned according to that key rather than the primary key. So obviously this is going to make our reads a lot faster because now ideally we would be able to have everything go to just one particular shard when performing our reads, so we're not making a kind of scatter-gather query there. But the cons of this approach are that now every single write has to go to multiple machines, because in all likelihood, the machine that I write to for our primary index is probably going to be a different machine than the one that is holding our row for its global secondary indexes. And so another challenge here is that we actually have to keep these two indexes in sync with one another. So what are our options? Option number one is something called two-phase commit. So we haven't introduced this concept yet, but the idea here is basically, well, two-phase commit is a way of making writes go through on multiple different machines at the same time and ensuring that they all apply them. It can't ever effectively work because at the end of the day, the network is completely asynchronous and there's no way to guarantee that two different writes absolutely go through, but this is pretty much the best we can do. So basically, we've got some node called the coordinator, and all the coordinator is going to do is it's going to reach out to all of the nodes that it wants to write to, and in the first phase, it's going to say, hey, prepare to accept some write. Once all the nodes say, okay, I'm prepared to do so, it's going to reach back out and say, okay, you can now commit the write. So simple enough, once that prepare phase is completed, basically all of these nodes that are prepared to accept the write can't really do anything else until they accept the write. They've pretty much guaranteed to the coordinator node that they will never reject the write in this situation, and so that is known as the commit point. We basically can't go back from there. So that's one option, but this is expensive, right? It requires multiple network round trips. We have to request a prepare, we have to get our prepare back, we have to commit, we have to hear that we're done. That is going to be a lot of work. What can we do instead? Well, if we're okay with having our indexes not perfectly in sync, but they'll eventually be in sync with one another, we can update our secondary indexes asynchronously. And so one option that we actually have here is we can use eventual consistency by basically saying, okay, first I'll update my primary index, and then whatever the node is that received the primary write, we'll go ahead and forward that write to basically the shard that is going to be updated for the secondary index. So for example, let's say I write to shard A because my user ID is number 1, and then my age is 100, so that's a really high age. Maybe that puts me on shard 10. Shard 1 is going to forward that write over to shard 10, and shard 10 will apply it. There's no guarantee on when that gets done. We know it'll happen eventually, but the point is if I now read from my secondary index, it may be a few seconds before I see that update actually propagated. Cool. Another piece to actually talk about here is SQL versus NoSQL. So again, I don't really like when people are like, oh, NoSQL is more scalable. But the reason that sometimes we'll say it is effectively that NoSQL basically just drops a lot of features that SQL offers in order to be more scalable when it comes to big data. And so really what it means is it's not necessarily that NoSQL databases are inherently more scalable, it's just that NoSQL databases support more scalable use cases because they don't really allow you to do all of these cross-shard writes, these cross-shard reads. They really encourage you, generally speaking, to try and keep all of your operations within a single shard so that you don't have to do something like a two-phase commit. And that's going to make your life a lot easier. For example, on Cassandra, you have this concept of a partitioning key, and the idea there is just like, hey, all of your writes have to be on a shard with the same partitioning key, and that way you're never doing something like a two-phase commit. Okay, so I think we've made it out of database hell. Let's go ahead and start talking about some other stuff. Number one is going to be batch processing. So basically, batch processing is just when we run a big batch job or a massive computation that's distributed over a massive data set. And so typically, these are run offline, which means they just have some sort of trigger. And in addition, it's not easy to write these, right? Or like, if you were to write one of these from scratch, you would have to account for the possibility that one of your worker nodes dies. You would have to account for the possibility that one of your worker nodes is doing a lot more computation than the other, and also you would want to make sure that you're avoiding any concurrency bugs associated with doing distributed computation. That's where batch processing frameworks come in. They basically handle all of this for you. Maybe you specify how you want to do something like sharding, but ultimately they are going to either checkpoint state or be able to restart jobs as necessary in order to ensure that they get done, even in the face of machine failures. And yeah, they're very useful. So if you hear about things like MapReduce or Spark, that's what we're talking about. There are reasons why Spark is better than MapReduce, but nonetheless, that's not the focus of this video. This is just very high level. Cool. The next thing that we're going to talk about is stream processing. So stream processing messages are basically generated by something known as a producer. So a producer is any sort of server. They're eventually going to be consumed by something known as a consumer. and then basically we use some sort of additional server that is responsible for routing messages from producers to consumers that is known as a message broker. And so what are basically the use cases of stream processing? Well, let's say we have a bunch of application events. We don't want to process them synchronously because maybe they would take too long to process and it would lead to request timeouts or something like that. That would be a really good example. If we have multiple different data streams that we want to join together, maybe we would do so in our consumer by briefly caching some of the events, waiting for the others, and then joining them together. And then also time-based aggregation as well. I want to find all the events that have come together within the last hour, and maybe I want to take the average of some number or some counter that they have. This is a really good way of doing so. Cool. So as far as stream processing goes, I mentioned that we have these brokers, and there are basically two types of them. Number one is what's known as the in-memory message broker. So the idea here is that we have a queue, we keep it in memory, and then we remove those messages when a consumer successfully reports that we've processed them. So basically, one of the unique things that in-memory message brokers can do is round-robin message delivery. So what this really means is that that queue, that single individual queue, can deliver messages to multiple different consumers at once. Now the nice thing about that is that it allows us to get a lot of throughput because now we have multiple consumers who can be handling messages at a time. Some of the cons are that we aren't necessarily processing all of these messages in order. When a message is sent to a consumer, it's briefly removed from the topic and kind of put in this potentially acknowledged area or this staging area, and then once it is ultimately acknowledged, it gets deleted. After some timeout, maybe it'll get added back to the queue because maybe the consumer failed or something like that. But the idea is we don't necessarily process these messages in order. And number two, and more importantly, is that if we are too slow to consume these messages and too many of them build up, we may run out of memory on the broker, and then things are going to break. Cool. The next piece of this is going to be the log-based message broker. So basically the log-based message broker is something like Kafka, if you ever heard about that. But the idea is that all we do is instead of keeping all these messages in memory in some sort of queue, we actually persist them all to what is effectively a write-ahead log on disk. And so that way, if I'm a consumer and I'm reading from this broker, the broker will actually keep track of the last offset of the message that I've last read. And so that way, within one single partition of one of these brokers, I'm just reading all of the messages sequentially from start to finish. And so a nice thing about this is that we get replayability. The reason is our messages are not actually deleted upon consumption. So what's really nice about that is, maybe for whatever reason we want to go back and check the value of our messages, we can actually read through this broker and do so again. So again, we're not doing this kind of round robining here of one partition to multiple consumers and each consumer handles a subset of the message. Within a partition, every consumer handles every single message, and so that is very much worth noting. Cool. As far as actual stream processing consumers go, this is starting to be a lot more popular, is to have stateful consumer frameworks. So I personally get shit on quite a bit in my videos for using these. However, I think they're very useful, and I will explain right now. So again, when you're consuming from these message brokers, it is very frequently the case that you need to build up some sort of state, right? If I'm doing time windowed aggregation, it means I need to cache all of the messages that I've seen in the last hour or something like that. And so what would really, really stink is if your consumer happens to fail and then all of those messages get lost. In theory, depending on the type of message broker, you may be able to replay those messages and build up your state again. And that's a really nice ability to have. But nonetheless, that can be very expensive if it's going to be the case that you've missed a ton of messages in the meantime, and now you're replaying a bunch of stuff and you're behind. So what these actual consumers will do, in addition to supporting all of these aggregations and joins and things like that, is that they will occasionally take their state and they will checkpoint it, right? So they'll take a state that they currently have, they'll take the corresponding offset in a log-based message broker that they've read from, and they'll put it in some other form of durable storage. So maybe they'll say, okay, at offset message number 20, I see that currently I've got 10 messages stored in my cache, and maybe here's what they are. So that way, if we fail and we start back up, we can read from that snapshot, get the exact state that we had before, and start again by reading at the log-based message broker from that offset, rather than having to read completely from the beginning and having to reestablish all of our state. So this is the type of thing that can save you quite a bit of time. Cool. Before we go ahead and get into the actual patterns of systems design interview problems, let's go ahead and talk about some other types of storage. So these are just like a few, I guess this is kind of like a potpourri of just random database systems that you'll often have to use during your interviews. And yeah, they're important to know if you don't. So number one is going to be a search index. This is useful when you want to perform something known as a full text search. It is not trivial to search for text content. So imagine, we have a bunch of tweets. We want to find all the tweets that say the word Jordan is handsome. So the way that you do that is you create something known as an inverted index. And of course, this has to scale over many, many different computers. But the idea is basically for every single word in that tweet, you go ahead and extract them all. And then you take all of the tweet IDs and say, okay, well, for word Jordan, here are all of the tweet IDs that contain it. And so that way I can quickly see, okay, if I'm searching for the term Jordan is handsome, let me find the entry for Jordan is and handsome and find all of the tweet IDs that are containing all three of those. Pretty simple way to do it. Number two is going to be distributed file systems. So this is something like Hadoop, but the idea here is it's basically like the file system on your computer scaled over multiple nodes. I guess the nice thing about this is that typically you can actually run computations on these files because ultimately the files themselves are stored on the computers, though it does really ultimately depend on the actual implementation of the file system. So if you are going to run something like a batch processing job, typically you'll store all of that data in something like a distributed file system and then do so from there. Next, we have graph databases. So I guess the idea here is sometimes you do need to be able to store a graph on disk because you want it to be durable, you want it to be accessible from many different servers, and this is not a trivial problem. So one possible implementation is called a non-native graph database, and this would be like using a SQL database to do it, where you basically represent all of the edges of a graph like a many-to-many relationship. So you have one table where it's like graph node ID 1, graph node ID 2, and then you have many different rows of that, and so that way you can quickly figure out for every single node in your graph all of its edges. The way that you make that read relatively fast is you add an index on that many-to-many table based on the node ID. The problem with that is that as the graph gets bigger, there are going to be more rows in that edges table, and if there are more rows in the edges table, it means that it's going to take us longer to read from it because indexes ultimately operate in logarithmic time. So even though it's not a full linear growth in terms of how slow it's getting, it is still getting slower as the graph grows. Sometimes we don't like that, thus leading to native graph databases. Native graph databases are basically just using pointers on disk, right? So rather than trying to get good data locality, they've just said, screw it, we're going to use pointers on disk. Now, maybe this is good for graph database tasks, but ultimately they're still kind of slow because using pointers on disk means that you're doing a lot of random reads, and doing a lot of random reads on disk are fairly slow. So maybe not the best solution, but if you have to have a graph database, perhaps this is the best way to do it. Cool. Next we'll talk about the object store. I guess the kind of prime example of this one would be something like Amazon S3. The gist is this is kind of not going to allow you to do compute locally on the data that you're storing. You basically just dump everything into a bucket and then you can go ahead and load it elsewhere and do compute there, but you do have to read it first. Because of the fact that this is storage that is kind of scaled up without compute, generally cheaper to store your stuff in, and so this is becoming really popular these days as storage solutions. And a lot of times for batch jobs, people will basically take data out of something like S3, load it into a distributed file system, and then run the batch job there, because perhaps it's cheaper. Cool. Next we have time series databases. So these are what they sound like, really good for time series data when your time series data is basically split up by two axes. One is like what is producing the time series data, and the other is the actual time range of it. The reason it's fast is because, one, we're using column-oriented storage, which we discussed earlier. A lot of this data is super similar to one another, so we can compress it really nicely. And two is that we can just be good about how we cache things, right? Like if I'm accessing a certain time range, I know that I'm probably going to access the next time range after that, and so we can be smart with that. We know it's going to be for the same sensor. And also the majority of inserts to this database are just going to be sequential. They're kept in the same order that they're added. And so you don't have to do anything too cheeky with writes. You can basically use something like a write-ahead log for all of your insertions. Okay, another piece of this to discuss are something known as geospatial indexes. Basically, these are really useful for finding all of the points within a certain distance of another point. So basically, geographic data is represented by a lat-long combo, And because these are two completely distinct fields from one another, there's not really a good way to build a database index that is going to allow me to find all of the points within, say, a circular radius from me. Indexes are really good for finding all latitudes within a certain range or all longitudes within a certain range. But if you look at the diagram that I made on the bottom left of the screen, if I'm trying to find all the points near the white dot, I can basically find really easily both of those rectangular areas that are in the black. So, all the points in a latitude near me and all the points in a longitude near me. However, that's going to be a lot of points, right? Because the globe is big and this spans a lot of area. And then eventually you're going to have to take all of those individual points and check whether they're actually close enough to the white dot. So that's too expensive. Instead, what we basically need to do is figure out a way to convert our latitude and longitude into a sort of one-dimensional key, so that way anyone with very similar one-dimensional keys is actually close to one another on our map. And this is kind of the philosophy between something known as like a geohash or a quad tree. And you can see that I've kind of annotated this structure on the left here. So on the left, we've got this big box with a bunch of smaller little boxes in it. And the way it starts is, okay, our largest box has, no geohash whatsoever. If you take one box and then you go to the top left of it, we basically take the existing ID and we add 0, 0 to it. If we go to the top right, we add 0, 1, bottom left 1, 0, bottom right 1, 1. So if we look at point C, you can see that the top right, top quarter box is 0, 1, and then the actual geohash of the box that point C is in is 0, 1, 0, 0, because it is the top left box of the top right box. And so by creating keys like this, what it means is that if we actually go ahead and organize all of the points on disk and sort their keys lexicographically, what it means is that we can basically do a very quick binary search to find one particular key value, and then all of the other points that are nearest to it in the database are going to have very similar keys. And so we basically take advantage of range queries here to go ahead and figure out all of the close points to another point. Finally, I believe finally, we've got coordination services. So basically the idea here is that occasionally it's not acceptable to lose our rights under any circumstances, right? And this is really going to be true for our application metadata. Who's the leader database? What partitions live where? Do I have a lock, or does this other server holding some sort of lock? Even if the database holding that information goes down, we don't want to lose that. That would be very bad. Our application is going to go to shit. So the way that we basically go ahead and ensure that this doesn't happen is we use something called a coordination service. And the reason this is good for a task like this is that they use an algorithm known as distributed consensus. So basically the idea here is that despite these algorithms allowing us to make sure we never lose data, even in the face of hardware faults, they're fairly slow to write to and read from. And as a result, we really only want to be using them for important application state. So just to demonstrate this, basically you've got a client that proposes writes to a leader. The leader then proposes writes to a bunch of followers, and the leader is doing so via two-phase commits, which we discussed earlier. The idea here is that a write is considered successful if a majority of the replicas in the cluster are actually saying, okay, this worked during the two-phase commit. So when the leader is sending writes to the followers, if 2 out of those 4 followers say, yes, I'm able to apply this, it can go ahead and continue. What this allows it to do is it basically means that if the leader is to go down, one of the followers that actually has all of the rights can go ahead and take over as the next leader. And it, of course, is going to need, yet again, a majority of approvals to do so. And it's kind of like the quorum logic from earlier, right? If you're always making sure that you're writing to and reading from a majority, you can always be sure that your data is up to date. And by using the two-phase commit, we avoid any sort of race conditions associated with that. Okay, totally forgot about this caching section. Let me go ahead and bang that out real quick before I take a break, because I'm starting to get sweaty here. Basically, the idea is that reading from disk is slow, disk is bad, let's use memory. Caches get filled up really easily, so how do we actually evict data when they're full? Typically, we'll use something like a least recently used policy, so LRU eviction. And then similarly to databases, caches can and should be replicated, and they should be sharded. So there are 3 different types of caching that we'll cover in this before we quickly cover CDNs, and let's go ahead and go through them. Number 1 is known as the write-through cache. If I'm an application, basically all I do is write to my cache and my database at the same time. Depending on your implementation of this, you may use a two-phase commit, which means writes are going to be pretty darn slow. At the same time, it means that your cache and your database are going to be kept up to date, which is very nice. Number 2 is the write around cache. In the write around cache, basically all you're going to do is you write first to the database, and then all reads you're going to attempt to make from the cache. And if the data that you want to read from the cache is not in there, the cache is going to go ahead and pull it from the database. This is nice in the sense that it's a faster write. The database is still the source of truth, which is good because the database should be your source of truth. And then finally, the kind of con of this approach is that cache misses are expensive, right? When you try to read from a cache and it doesn't have the data, now you still have to go to the database, and you basically did 2 reads for 1, so that's inconvenient. Then finally, we are going to go ahead and have the write back cache. So in the write back cache, basically an application is going to make multiple writes directly to the cache, and at some point the cache is asynchronously going to sync up with the database. So this is really nice because you're just basically only writing to memory. That's super fast. At the same time, if I'm a different application and I'm reading from the database, I'm not going to see the writes that are in the cache. That's bad. Okay, a final piece of kind of caching information we'll talk about is content delivery networks. These are basically geographically distributed caches for static content, like pictures or videos or anything like that. If you have stuff in S3 that you want to store or basically serve to multiple users around the world, sometimes it makes sense to do so from a CDN. Okay, load balancing. I think I'm getting here, but I actually just can't even remember my own table of contents, which is why I'm still going at this. Basically, in any large application, we have to be able to do something called horizontally scaling, which is when you take one server and you make a bunch of them, because ultimately that one server is going to get too many requests. So, if I have like a sign-in service, maybe I need 100 sign-in services. And a load balancer is the piece of technology that's going to take me, a user, and tell me which sign-on service I'm actually using. So basically they can operate on multiple different policies. One example would be round robin. We basically just randomly choose, you go on a loop and you choose the next one that didn't previously serve the request. Another would be using consistent hashing like we spoke about before. Sometimes it's really, really useful when the same request or similar requests are being routed to the same exact server, because maybe that server has some cached information that's going to make that request a lot faster. We can do this hashing on things like your IP address, so any like networking related information known as layer 4 load balancing, or application specific information where you'd actually have to read the packet itself, and that would be called layer 7 load balancing. Cool. As far as fault tolerance goes for load balancers, because they too can become single points of failure and go down, I guess there are a couple of ways that you can run them. One is the active-active configuration, where you're running multiple different load balancers at once. We probably use some coordination service so that clients can actually read from the coordination service, figure out what load balancers they have access to, and then randomly route a request to one of them. Number 2 is active-passive configuration, where you're basically doing something similar. Every load balancer is registered with a coordination service, but only one of them is actively routing requests. And then if that goes down, the coordination service is going to report that it's down via some sort of heart beating with it. And then the passive one is going to say, okay, I'm the active one now, all requests can go to me. All right, my throat was starting to hurt and I was starting to get a little bit sweaty, but let's go ahead and finish this thing off. Here we go. Systems design interview patterns. Like I mentioned, a lot of these problems can really just be broken down into common themes. Let's go ahead and break them down. Number 1 that I see a lot is contending updates. This is basically when you have a bunch of writes to the same key, so many so that it's not simple to just do them on one node because you're just going to have too much lock contention. Examples here would be building out a distributed counter, maybe dealing with order inventory on something like Amazon for a popular product. And I guess, the naive solution is you just do everything in the same database and deal with contention. Might not be acceptable. What would be better is perhaps using multiple database leaders, and then basically using something like, kind of that automatic merging logic that we discussed before to go ahead and eventually make these guys consistent. This works really nicely for something like a distributed counter or a set, or you could use stream processing, right? So you put everything in something like a Kafka queue, you handle it downstream by a consumer, maybe handle them in a mini batch if we want to use Spark streaming instead. And then you'll go ahead and make writes to the database such that you're doing so with multiple batches at a time. Fewer writes means less contention. Next, we have derived data. So let's say we have 2 data sets that we want to keep them in sync with one another. We discussed a couple of examples of this already, one being the global secondary index. Basically, if we have maybe another data set which is being updated by one particularly slow database, but we want to make a faster read-only view on the data, this would also be another good use case. So for something here, what we could do is, naively a two-phase commit, and this may be necessary if we need to keep them perfectly in sync. However, what might be better is something like change data capture. Change data capture is pretty simple. It is something that works with a lot of different databases. And what it does is it takes all of the updates to a particular database, pipes them into a log-based message broker, and then that broker consumer can do any transformations that are necessary, pipe all of the changes from there into another database. Cool. So this is going to allow us to be eventually consistent. I'm sorry, as you guys can see, my throat is dying. So we've got some sort of source database. It has all of its transaction logs. It puts that into our change data capture framework, which is really just stream processing, and then they get sank into our target database. Next, we've got fanout. Fanout is one that you should know really, really well because it comes up probably in 50% of these problems. The idea here is that rather than do a really expensive read query, because we have a lot of read-optimized applications in real life for users, what we want to do is do more work on the write path and basically take our data that we're about to write and deliver it directly to all of the users who are interested. Examples of this include push notifications, a social media newsfeed, something like figuring out who our mutual friends are every single time that we make a new single friend connection, and also stock price delivery, right? We've got many interesting parties when the price of, say, a Google stock goes up or down by $1. So one option is we can, deliver all of this data to all interested users synchronously by virtue of, doing it in some sort of API. Maybe we hit an endpoint, we go hit 100 other servers to deliver the message there, and then we report back to the user. But the majority of the time, this is going to time out because there are too many places to reach out to. So we probably have to do it asynchronously in the background. What a surprise, we're using stream processing again. You guys shit on me for using Flink all the time, except literally the majority of these problems, it makes the most sense to use stream processing. And when you're using stream processing, you're often better off using a stream processing framework for better fault tolerance. Anyways, the idea here is you want to put your message in a log-based message broker. You have some sort of consumer that receives it. It figures out where the message needs to be sent to, and then it does so accordingly. What does that look like? Well, basically, like I said, user posts it. We've got some sort of broker that has all of the tweets, and then, right after that broker, someone is consuming all of those messages and delivering it to some sort of cache for every interested user. Now, one caveat of this problem is that we'll often have is kind of the popular message problem, right? So let's imagine I'm Jordan Has No Life, very famous YouTuber, and I've got many, many Twitter followers. I think I have maybe 50 at most. But okay, let's imagine I'm Ronaldo and I have 1 million Twitter followers. The idea is that you can't really deliver this to 1 million Twitter caches. And so as a result, for messages like that, the stream consumer is going to notice how many places it has to deliver it to, and it's going to instead opt to just deliver it to some sort of popular message cache. This way, we ultimately build out a hybrid approach where you basically have all of the messages that are not super popular sent to all of the individual users that are interested in them, and for popular ones, those same individual users can occasionally pull from the popular cache and generate the necessary state there. Cool. Another pattern that we see come up all the time is proximity search. Basically, this is find all of the close points in a database to you. We already discussed this, right? You want to be using a geospatial index. Examples where this comes up is Uber, Yelp, Airbnb, Find My Friends. I've seen literally every variation of this problem on YouTube because people just want to steal views. The idea is that you can build indexes on latitude or longitude, but like we already mentioned, that's a problem. That's not going to work. So what you use instead is a geospatial index. Now, of course, there's a ton of data in these database tables, and you need to do some sort of sharding. How do we shard? Well, typically you want to shard kind of based on that geospatial bounding box, right? That being said, not all geospatial bounding boxes are equal. There's a lot more data points in some place like New York than there might be somewhere like Wyoming. And so you have to account for that. Ultimately, what you'll do is you'll probably make a bunch of very, very small partitions and then potentially dynamically move those partitions to equal out the load over time as you get a better sense of where the load is actually going to and coming from. Next, we have job scheduling. This one comes up a lot in the literal build a job scheduler problem, and it also comes up in like the Netflix and YouTube problem, because when you upload a video, you have to enqueue a bunch of jobs to encode it in many different resolutions, and you want to probably be doing all of those offline rather than synchronously. In that way, it's kind of also a fan-out problem, but same idea. So basically, the gist here is we've got a bunch of agnostic tasks that we need to get run. We don't care where they run, it just needs to happen. So Our two options are as follows, right? We have two types of brokers. We know we want to do this asynchronously. If we use a log-based message broker, what we would probably end up doing is we'd have to make a bunch of partitions of it, and then you would have a consumer reading from each partition, right? One of the workers in our cluster that runs the jobs. So the problem with that is we know that messages in a log-based message broker are read in order. And so that would mean that if there's one particularly slow job in a partition of a message broker, it means that we are not going to be able to run all of the jobs behind it. They're just going to get completely bottlenecked. And it could be the case that the other workers are going to have nothing to do in their particular partition of the log-based message broker. So what would be a better approach is to actually use an in-memory message broker here and use that to basically round robin all of the jobs from worker to worker. A worker can then pull a job off the queue the moment that it becomes available. One more pattern to discuss here is going to be aggregation. This is basically, okay, we've got a bunch of messages. They're being sent out by millions of different servers. They're probably going to be aggregated on some sort of key or maybe joined with other messages. How do we want to do this? Well, example situations are metrics or logs, right? If I'm publishing a bunch of metrics, but the metrics for a particular key can come from many different servers, maybe I want to aggregate them and make sure they're in the same file. Same thing for logs. If we have multiple components of like a particular job that are all being run, and then once they're done, they need to be aggregated. This is another example. Data enrichment. If I'm publishing a bunch of messages and they need to be joined with a bunch of other published messages, this is an example. One option is you just put everything in a database, corresponding to the server it's coming from, and then you run a batch job and do all the joins you need. That does work. Wow, I'm really losing my voice. That does work. However, it's pretty naive in the sense that it's going to take you a lot longer to actually see the results that you want to see. You're going to do a lot of work in order to get that data. Number two is you can do stream processing, right? So if you're smart about how you actually partition this data and you partition your log-based message brokers on the actual key that you want to do the aggregation on, then you can actually send those messages to the proper broker. They can be consumed by the proper stream processing instance, perhaps Flink, perhaps Spark Streaming, anything like that. And then from there, you can export them to wherever they need to go. Okay, another pattern to talk about is idempotence. Basically, you have some task, you're running it, you don't want to see the output of it more than once. I think some good examples of this would be, okay, if we're running a job in a job scheduler, how do we ensure that the output of that job is only reflected once in our system? Number two is, let's imagine like I'm Amazon and I'm sending out a bunch of confirmation emails to users when they make an order. How do I make sure that doesn't happen multiple times? Systems can fail, they come back up, they may retry their jobs. We don't want to see the result of it more than once. Sometimes in this situation, you have to do a two-phase commit, right? Like if I'm not the person who controls the email service and, I'm not controlling a user's inbox, it's very hard for me to actually stop myself from sending a second email. That being said, one way that you can potentially do this is using something known as an idempotency key. So the computer potentially that is going to run this job and may accidentally run it again can use basically a unique ID associated with the job that it's going to run and check whether it's seen that before. That might mean putting that key in a database and reading from the database, or depending on where you're going to run the job, if you know that you're always running it on a certain system, maybe you can cache it locally. Another kind of thing to note here, in addition to idempotency keys, you also have this concept called fencing tokens, where fencing tokens is similar to idempotency keys, but it's actually on the receiving side of the message. So rather than kind of on the side of the computer doing the job, it's on the side that is receiving the output of the job. And basically, if it sees that same unique key associated with the job, it can reject it and say, hey, I've already seen this before. I don't want to consider this output. Okay, I think the last pattern that we've got here to discuss is going to be durable data. So again, we've already kind of discussed this with coordination services. You have a bunch of data that can't be lost once it's written. Good example of this would be something like financial transactions. So one option is you have a bunch of database replicas and you replicate to all of them synchronously. That'll work, but it means that if any of them go down, you can't submit any writes, your system is not fault tolerant. So our really only solution here is to use, yet again, some sort of distributed consensus algorithm. Consensus is going to allow us to build a distributed log, and as a result, we can basically build a database view on top of that distributed log. Even better than that, however, would be actually coupling this with something like change data capture, because our log itself is really nice in the sense that it ensures all of our data is persisted, even in the sense of hardware failures. However, what's nice about change data capture is that for something like a financial transaction, maybe you're writing all of your data into a ledger, it would be a lot better if a user individually can really quickly find all of their own transactions in a list. And so rather than just reading through the entire ledger and finding all the transactions that apply for a given user, what we can do is make a user-specific index, and we can do so with change data capture, and we already discussed how that works. Okay, guys, that's all of it. My voice is gone. I feel like shit. But yeah, I hope you enjoyed the video. I understand that this is really high level, kind of hand wavy for a lot of the topics that we discussed here. And my goal is not to go super in depth on these topics. That's why I have literally 200 plus videos on this channel, is to go ahead and do all of that. So I do hope that if, this kind of interested you, or you were like, I didn't really understand one particular topic Jordan was talking about, that you'll actually go and find the videos on my channel that relate to it, because all of these are explained in a lot more depth elsewhere on here. Besides that, again, thank you guys so much for 50,000 subscribers. This channel has supplied my life with a purpose that I didn't really know I could have, and I've derived a much bigger sense of meaning than I thought I could through just learning a lot about computer science. Not only do I feel like I'm getting to learn a ton, and that's really rewarding, hearing your guys' success stories has made all of this more than worth it for me. And yeah, I'm just shocked and appalled to be here. I'm truly humbled by all of you. Yeah, that's it. This is amazing. This is great. I'm going to keep doing it. I'm having a lot of fun with this channel, and I don't plan on stopping. Have a great day, guys.